All right, let's talk about something that's like the bedrock of pretty much all programming. It's simple, it's incredibly powerful, and trust me, it is everywhere. We're talking about the array. Have you ever stopped to think about how your computer juggles, I don't know, a million emails at once? Or how a video game can keep track of every single enemy, bullet, and piece of scenery on the screen? I mean, how does it handle all that data without just melting down?
Well, the answer isn't some super fancy, cutting-edge new thing. Nope. It's actually one of programming's oldest and most fundamental tools, something that's been at the core of computing for a very long time.
Okay, so let's get right into the problem. Imagine you need to keep track of, say, 100 test scores for a class. Are you going to sit there and type out score 1, score 2, score 3, all the way up to score 100? No way! That would be absolutely insane. And then trying to do anything with that, like sort the scores from highest to lowest? Forget it. Total nightmare. And this is where the array just waltzes in and saves the day. It's such an elegant solution, right? You get one single container with one single name that can hold all those values. Now today, we're going to zero in on the classic C array. Why? Because if you really get how this thing works, you'll understand so much more about how computer memory and even more complex data structures operate. So, what is an array, really? At its heart, it's just a box, a container for a bunch of items. But there's a big rule. Everything inside has to be the same type. Think of it like a street where all the houses are identical, and each one has a number on the door. To get to a specific house, you don't need a crazy map. You just need its number. Or in our case, what we call its index.
And what's so wild about the C array is just how basic it is. All the items, we call them elements, are the same type. You get to them using an index. And this is a big one. You got to remember this. The first element is always at index 0. Not 1, 0. But here's the real kicker. The C array is kind of dumb. It doesn't do anything for you. The programmer, that's you, is responsible for literally everything. You have to remember how big it is, and you have to make sure you don't accidentally try to look for an element that isn't even there.
So that responsibility forces you to make a really big decision right up front. Do you know exactly how many items you're going to need before your program even starts running? Or is that something you're only going to find out while it's in motion?
This slide just perfectly lays out the trade-off, doesn't it? The static array, that's your pre-built bookshelf from the store. You know the size, it's set in stone before you even run the code, and that's that. The dynamic array is more like you're building the shelf yourself. You decide how big it needs to be while the program is running. It's more flexible, but once you've built it, that size is also fixed. And they even live in different neighborhoods in your computer's memory. Static arrays are on the stack, which is super fast and temporary. Dynamic ones are on the heap, which is for stuff that needs to be more flexible. It's a huge difference that really impacts how your program runs.
Okay, so arrays are awesome. We get that. But because they're so basic, they have some, let's call them surprising limitations. And believe me, this is where a lot of people, especially when they're starting out, get into trouble.
Okay, here's the biggest gotcha. You can't just do things to the whole array at once. These are called aggregate operations. You can't just say, hey computer, copy this whole array over there, or tell me if these two arrays are exactly the same. Nope. With a C array, you have to do pretty much everything, one single element at a time. It's all manual.
And that brings us to a classic trap. You might think, oh, I'll just copy an array with an equal sign. Easy. But if you do that, oh boy, you are not going to get what you expect. You are not copying the data, not even close.
What's actually happening is something called a shallow copy. What you've done is you've created two names, original array and copied array, but they are both pointing to the exact same spot in memory. They're like two different street signs pointing to the same house. So if you go in and repaint the walls using one street sign, the house is still repainted if you get there using the other one. There's only one set of data.
So if you want a real copy, a totally separate duplicate of the data, what we call a deep copy, you've got to roll up your sleeves and do it yourself. It's a three-step process. First, you make a brand new empty array. Second, you make darn sure it's big enough to hold everything. And third, you have to go through the original element by element and copy each one over by hand.
So yeah, they have their quirks. But despite all that, arrays are still the absolute backbone of so many things we use. So let's shift gears and look at where this simple little box shows up in the real world.
Here's a fantastic example, a 2D array. What is that? It's literally just an array of arrays.
That's it. And this simple idea lets you create a grid, with rows and columns. It's perfect for a chessboard or a spreadsheet or, a tic-tac-toe board, just like this one. You can see how board for row 0, column 2 gets you that O in the top right. Super intuitive.
And you absolutely need arrays for one of the most common jobs in all of computing, sorting stuff. Let's take a simple sorting method called bubble sort. Now, full disclosure, it's super slow, but it really shows how this works. You just go through the array, look at two elements next to each other, and if they're in the wrong order, you swap them. Then you move to the next pair and do it again and again and again until the whole thing is sorted. You just flat out can't do that without an array to hold all the data.
Okay, but now the story takes a bit of a dark turn. That primitive nature of the C array, the fact that it has 0 built-in safety nets, well, that means a tiny, simple mistake can turn this handy little box into a massive, catastrophic security hole.
And I am not exaggerating one bit. People who know this stuff describe this exact problem as, and I quote, one of the most dangerous security flaws that lets hackers completely control a program. That's a big deal.
This flaw has a name. It's called a buffer overflow. See, an array is a buffer. It's just a fixed chunk of memory. An overflow is exactly what it sounds like. It's what happens when you try to shove more data into that buffer than it was built to hold. The analogy is perfect. It's like pouring a whole gallon of milk into a tiny pint glass. The extra stuff has to go somewhere, right? And it spills out, corrupting everything around it in the computer's memory.
And here's the really scary part. That spillage isn't just a random accident that makes the program crash. A smart attacker can craft that overflowing data on purpose. They can make it overwrite important parts of your program, hijack its logic, and, well, basically take complete control. It all starts with one simple mistake, but the consequences can be absolutely devastating. So, this brings us to the really crucial point. Look, modern languages have much safer tools now, like vectors in C++, that take care of all this messy stuff for you. But even with those tools, understanding the raw, bare-bones C array is still absolutely essential. It's a foundational idea. Okay, so what are the big takeaways here? Let's break it down. 1. Arrays are just containers for stuff of the same type. Simple. 2. The old-school C array is primitive. It's on you, the programmer, to manage it correctly. 3. If you understand arrays, you understand a huge piece of how computer memory works. And 4, and this is a big one, if you get it wrong, you can create some of the worst security holes imaginable.
And that leaves us with one last question to chew on. We have all these safer, smarter, modern tools that stop these problems from ever happening. So if that's true, why is it still so incredibly important for every single programmer to understand on a deep level how this simple, primitive, and sometimes dangerous little box actually works?